Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 7, Coordinate Systems in 2- and 3-Dimensional Forms. Section 63, Homogeneous Coordinates in the Plane. In the analytic representation of points and lines developed in the preceding sections, the points on the line UV equal O and the lines on the point O were left unconsidered. To remove the exceptional character of these points and lines, we may recall that in the case of a similar problem in the analytic representation of the elements of a one-dimensional form, we found it convenient to replace the non-homogeneous coordinates x of a point on a line by a pair of numbers x1, x2, whose ratio x1 divided by x2 was equal to x not equal infinity, and such that x2 equals 0 when x equals infinity. A similar system of homogeneous coordinates can be established for the plane. Denote the vertices O, U, V of any triangle, which we will call the triangle of reference, by the coordinates 0, 0, 1, 0, 1, 0, 1, 0, 0, respectively, and an arbitrary point T not on a side of the triangle of reference by 1, 1, 1. The complete quadrangle, OUVT, is called the frame of reference of the system of coordinates to be established. Footnote: frame of reference is a general term that may be applied to the fundamental elements of any coordinate system. The lines UT, VT, OT meet the other sides of the triangle of reference in points which we denote by 1 sub x equal to 1, 0, 1, 1 sub y equal to 0, 1, 1, 1 sub z equal to 1, 1, 0, respectively, figure 82. We will now show that it is possible to denote every point in the plane by a set of coordinates x1, x2, x3. Observe first that we have thus far determined 3 points on each side of the triangle of reference, namely 0, 0, 1, 0, 1, 1, 0, 1, 0 on OU, 0, 0, 1, 1, 0, 1, 1, 0, 0 on OV, and 0, 1, 0, 1, 1, 0, 1, 0, 0 on UV. The coordinates which we have assigned to these points are all of the form x1, x2, x3. The 3 points on OU are characterized by the fact that x1 is equal to 0. Fixing attention to the remaining coordinates, we choose the points 0, 0, 1, 0, 1, 1, 0, 1, 0 as the fundamental points 0, 1, 1, 1, 1, 0 of a system of homogeneous coordinates on the line OU. If in this system a point has coordinates LM, we denote it in our planar system by 0, LM. In like manner, to the points of the other 2 sides of the triangle of reference may be assigned coordinates of the form K0M and KL0 respectively. We have thus assigned coordinates of the form x1, x2, x3 to all the points of the sides of the triangle of reference. Moreover, the coordinates of every point on these sides satisfy one of the 3 relations x1 equals 0, x2 equals 0, x3 equals 0. Now let P be any point in the plane not on a side of the triangle of reference. P is uniquely determined if the coordinate of its projections from any 2 of the vertices of the triangle of reference on the opposite sides are known. Let its projections from U and V on the sides OV and OU be K0N and 0 L'N' respectively. Since under the hypothesis none of the numbers K, N, L'N' is 0, it is clearly possible to choose 3 numbers x1, x2, x3 such that x1 is to x3 as K is to N, and x2 is to x3 as L' is to N'. We may then denote P by the coordinates x1, x2, x3. To make this system of coordinates effective, however, we must show that the same set of 3 numbers x1, x2, x3 can be obtained by projecting P on any other pair of sides of the triangle of reference. In other words, we must show that the projection of P equal to x1, x2, x3 from O on the line UV is the point x1, x2, 0. Since this is clearly true of the point T equal to 1, 1, 1, we assume P distinct from T. Since the numbers x1, x2, x3 are all different from 0, let us place the ratio x1 to x3 equal to x and x2 to x3 equal to y, so that x and y are the non-homogeneous coordinates of x1, 0, x3, and 0, x2, x3, respectively, in the scales on OV and OU, defined by O equal 0 sub x, 1 sub x, V equal to infinity sub x, and O equal 0 sub y, 1 sub y, U equal infinity sub y. Finally, let OP meet OU in the point whose non-homogeneous coordinate in the scale defined by U equal 0 sub z, 1 sub z, V equal to infinity sub z is z, and let OP meet the line 1 sub x u in A. We now have infinity sub z, 0 sub z, 1 sub z, z is perspective with center O to 1 sub x, 0 sub z, t A, which is perspective with center V to 0 sub y, infinity sub y, 1 sub y, c, where c is the point in which VA meets OU. This projectivity between the lines UV and OU transforms 0 sub z into infinity sub y, and infinity sub z into 0 sub y, and 1 sub z into 1 sub y. It follows that c has the coordinate 1 divided by z in the scale on OU. We have also infinity sub x, 0 sub x, 1 sub x, x is perspective with center U to z, 0 sub x, AP is perspective with center V to infinity sub y, 0 sub y, 1 divided by z, y, which gives x equal to the net of rationality, r of infinity sub x, 0 sub x, comma, 1 sub x, x, equal to r of infinity sub y, 0 sub y, comma, 1 divided by z, y, is equal to zy. Substituting x equal the ratio x1 to x3 and y equal the ratio x2 to x3, this gives the desired relation z equal the ratio x1 to x2. The results of this discussion may be summarized as follows. Theorem 2, definition. If P is any point not on a side of the triangle of reference, OUV, there exist three numbers x1, x2, x3, all different from 0, such that the projections of P from the vertices OUV on the opposite sides have coordinates x1, x2, 0, x1, 0, x3, 0, x2, x3, respectively. These three numbers are called the homogeneous coordinates of P, and P is denoted by x1, x2, x3. Any set of three numbers, not all equal to 0, determine uniquely a point whose homogeneous coordinates they are. The truth of the last sentence in the above theorem follows from the fact that if one of the coordinates is 0, they determine uniquely a point on one of the sides of the triangle of reference, whereas if none is equal to 0, the lines joining U to x1, 0, x3 and V equal to 0, x2, x3 meet in a point whose coordinates, by the reasoning above, are x1, x2, x3. Corollary. The coordinates x1, x2, x3, and kx1, kx2, kx3 determine the same point if k is not 0. Homogeneous line coordinates arise by dualizing the above discussion in the plane. Thus, we choose any quadrilateral in the plane as frame of reference, denoting the sides by 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, respectively. The points of intersection with 1, 1, 1 of the lines 1, 0, 0, 0, 1, 0, 0, 0, 1 are joined to the vertices of the triangle of reference opposite to 1, 0, 0, 0, 1, 0, 0, 0, 1, respectively, by lines that are denoted by 0, 1, 1, 1, 0, 1, 1, 1, 0. The three lines 1, 0, 0, 1, 1, 0, 0, 1, 0 are then taken as the fundamental lines 1, 0, 1, 1, 0, 1 of a homogeneous system of coordinates in a flat pencil. If in this system a line is denoted by U1, U2, It is denoted in the planar system by u1, u2, 0. In like manner, two lines on the other vertices are assigned coordinates of the forms 0, u2, u3, and u1, 0, u3, respectively. As the plane dual of the theorem and the definition above, we then have at once Theorem 2' definition. If L is any line not on a vertex of the triangle of reference, there exist three numbers u1, u2, u3, all different from 0, such that the traces of L on the three sides of the triangle of reference are projected from the respective opposite vertices by the lines u1, u2, 0, u1, 0, u3, 0, u2, u3. These three numbers are called the homogeneous coordinates of L, and L is denoted by u1, u2, u3. Any set of three numbers, not all 0, determine uniquely a line whose coordinates they are. Homogeneous point and line coordinates may be put into such a relation that the condition that a point x1, x2, x3 be on a line u1, u2, u3 is that the relation u1, x1 plus u2, x2 plus u3, x3 is equal to 0 be satisfied. We have seen that if x1, x2, x3 is a point not on a side of the triangle of reference, and we place x equal to x1 divided by x3 and y equal to x2 divided by x3, the numbers x, y are the non-homogeneous coordinates of the point x1, x2, x3, referred to OV as the x-axis and to OU as the y-axis of a system of non-homogeneous coordinates in which the point t equal to 1, 1, 1 is the point 1, 1, OUV being used in the same significance as in the proof of Theorem 2. By duality, if u1, u2, u3 is any line not on any vertex of the triangle of reference, and we place u equal to u1 divided by u3 and v equal to u2 divided by u3, the numbers u, v are the non-homogeneous coordinates of the line u1, u2, u3 referred to two of the vertices of the triangle of reference as u-center and v-center respectively, and in which the line 1, 1, 1 is the line 1, 1. If now we superpose these two systems of non-homogeneous coordinates in the way described in the preceding section, the condition that the point xy be on the line uv is that the relation ux plus vy plus 1 is equal to 0 be satisfied. Theorem 1. It is now easy to recognize the resulting relation between the systems of homogeneous coordinates with which we started. Clearly, the point 0, 1, 0 is equal to u is the u-center, 1, 0, 0 equal v is the v-center, and 0, 0, 1 equal to o is the third vertex of the triangle of reference in the homogeneous system of line coordinates. Also, the line whose points satisfy the relation x1 equals 0 is the line 1, 0, 0. The line for which x2 equals 0 is the line 0, 1, 0, and the line for which x3 is equal to 0 is the line 0, 0, 1. Finally, the line 1, 1 equal to 1, 1, 1, whose equation in non-homogeneous coordinates is x plus y plus 1 equal to 0, meets the line x1 equals 0 in the point 0, negative 1, 1, and the line x2 equals 0 in the point negative 1, 0, 1. The two coordinate systems are then completely determined. Figure 83. It now follows at once from the result of the preceding section that the condition that x1, x2, x3 be on the line u1, u2, u3 is u1, x1 plus u2, x2 plus u3, x3 is equal to 0. If none of the coordinates x1, x2, x3, u1, u2, u3 is 0. To see that the same condition holds also when one or more of the coordinates is 0, we note first that the points 0, negative 1, 1, negative 1, 0, 1, and negative 1, 1, 0 are collinear. They are, in fact, figure 83, on the axis of perspectivity of the two perspective triangles O, U, V, and 1 sub x, 1 sub y, 1 sub z, the center of perspectivity being T. It is now clear that the line 1, 0, 0 passes through the point 0, 1, 0. The line 0, 1, 0 passes through the point 1, 0, 0. The line 1, 1, 0 passes through the point negative 1, 1, 0. There is thus an involution between the points x1, x2, 0 of the line x3 equals 0 and the traces x1 prime, x2 prime, 0 of the lines with the same coordinates, and this involution is given by the equations x1 prime is equal to x2, x2 prime is equal to negative x1. In other words, the line u1, u2, 0 passes through the point negative u2, u1, 0. Any other point of this line, except 0, 0, 1, has by definition the coordinates negative u2, u1, x3. Hence, all points x1, x2, x3 of the line u1, u2, 0 satisfy the relation u1, x1 plus u2, x2 plus u3, x3 equals 0. The same argument applied when any one of the other coordinates is 0 establishes this condition for all cases. A system of point and a system of line coordinates, when placed in the relation described above, will be said to form a system of homogeneous point and line coordinates in the plane. The result obtained may then be stated as follows. Theorem 3. In a system of homogeneous point and line coordinates in a plane, necessary and sufficient condition that a point x1, x2, x3 be on a line u1, u2, u3 is that the relation u1, x1 plus u2, x2 plus u3, x3 equals 0 be satisfied. Corollary. The equation of a line through the origin of a system of non-homogeneous coordinates is of the form mx plus ny equals 0. Exercises. 1. The line 1, 1, 1 is the polar of the point 1, 1, 1 with regard to the triangle of reference, chiefly page 46. 2. The same point is represented by a1, a2, a3 and b1, b2, b3 if and only if the two road determinants of the matrix a1, a2, a3, b1, b2, b3 are all 0. 3. Describe non-homogeneous coordinates and homogeneous systems of line and plane coordinates in a bundle by dualizing in space the preceding discussion. In such a bundle, what is the condition that a line be on a plane?
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.